Hey everyone, so my name is Zach Vines, and what I want to go over today is how to calculate a test statistic whenever we're dealing with two sample hypothesis tests. So before, by the time you've gotten up to this point in statistics, you've likely calculated test statistics for one sample hypothesis test, where for those one sample tests, we had, if it was a mean-based problem, you would take your sample mean, your x bar, minus your population mean, mu, and divide it by your standard error, which is your standard deviation, s, divided by square root of n, which is the number of trials in your sample. Or if you're dealing with a proportion-based problem, you would take your sample proportion f, subtract out your population proportion pi, sometimes it's p, depending on what class you're in, but either way, it's the population proportion variable, divided by big square root, pi times 1 minus pi divided by n, and that's the standard error for a proportion-based problem. So overall, the base formula for the one sample test statistics was your sample information minus your population information divided by your standard error. Just how you got that standard error was a little bit different based on the type of problem you had, and the sample and population information would be a little bit different as well based on the information you're provided. So for a two-sample test statistic, when we're calculating that, hold on to this base formula. It's very, very similar in that you're going to take sample information minus population information and divide by a standard error. But just like how the sample and population information and the standard error, all three of those things, are different between a mean versus a proportion-based problem, they're going to be also different from one another when we're dealing with a two-sample problem. So one more thing to consider is that when we're dealing with a two-sample hypothesis test, we're going to have one of two types of those tests, where we have either independent samples, meaning that they're two totally different samples that we're doing completely different tests on, two different treatments. So an example I gave of that in a previous video was that if we have a situation where we have some treatment we think might work, and we want to test the effectiveness of it, we give one group a placebo, one group the treatment we think might work. So it's two different groups with each with their own specific treatment. Those are independent samples. Whereas when we're dealing with a matched paired sample, we have one group that we introduce a treatment to, and we see what changed before the treatment was introduced versus after. So an example I gave of that in a previous video was if we have a group of people that we want to lose weight. We take their weight before we give them this diet. Then they perform the diet, they eat how they should, they do everything they need to, and then we see what the weight was afterwards so we can see the change in their weight and test how effective the diet was. So you can see it's one group that we introduce a treatment to, see the before and after on that, and those are the two different types. So next we're going to get into the actual formulas to set those up, but hold on to the fact that this base formula is the key to figure out any of these test statistic formulas. It's just a little bit different because there's two samples, and then we need to further distinguish between them based on if it's an independent samples test or a matched paired sample, so let's do that right now. Okay, so what we're going to talk about first is how to find the test statistic whenever we have a mean-based problem and they're independent samples. So not a matched paired sample where we introduce a treatment and it's a before and after. We have two different groups, two independent groups with their own treatments. Here's how you solve for it. First thing I want to say is that depending on the class you have, and I've had different ones where this is a different benchmark between the two, you may not have to worry about this formula right here. Oftentimes, whenever you're dealing with a mean-based problem that is an independent sample, it's just assumed that you have to do these steps right here where we pool the variance. Sometimes it's depending on whether or not your sample size is larger than 30, greater than equal to 30, or simply less than 30. So just make sure that you're following the appropriate benchmark for your particular class. But kind of the overall idea is that if you're looking at your sample and the number of trials in your sample, the thing that you're testing, you do that 30 or more times, the way you find your test statistic, which is going to be either a z or a t value. It's the same formula for either one. It's just what you do with that value is different later on, depending on whether or not it is a z or a t. The formula for that is simply going to be this. So remember the base formula we said before. It's your sample information minus your population information divided by your standard error. So it's the same thing here where we have our sample information, x bar 1 minus x bar 2. It's not simply x bar minus mu like it was before because we have two different samples. Each one has their own x bars, and thus you would need to take both of those into account when talking about the sample portion of it. So the x bar 1 minus x bar 2 is the sample, minus mu1 minus mu2, the population, and that's just whatever it is you're hypothesizing about. So when you set up your hypothesis test, and we have plenty of other videos talking about how you set up hypotheses for these two sample test statistics, but by the time you get here, you've probably already seen those or are familiar with that material. If not, definitely check out the playlist under stats under the channel. But whatever it is that you have in your hypothesis, the number that relates to that is what you put in for mu1 minus mu2. Divide that by big square root, the first sample's standard deviation squared divided by n1, the number in that sample, plus the standard deviation of the second sample squared divided by the number in that sample. That's just if you have to use that benchmark. That might not even be a relevant formula as far as your class is concerned. Either way, this one is going to be relevant no matter what. So the steps you have to do here is that you're essentially having to take these steps so you can funnel it down into your overall test statistic formula, but you need to, sort of crawl before you walk. Start by getting this, which funnels into this, which funnels into this. So start off by finding your pooled sample variance. So it's this SP squared right here, and it's just, again, a formula you plug into. You do N1 minus 1, which is the number of trials in the first sample, minus 1 times the standard deviation of the first sample squared, plus N2 minus 1 times S2 squared. Divide all of that by N1 plus N2 minus 2. So in general, maybe at this point you've heard of degrees of freedom before, where that's often N minus 1. Well, in this situation, when we have two different N's, we're doing N minus 1, but we're doing it for both samples. So N1 minus 1 and N2 minus 1, you combine those and that gives you the degrees of freedom. Or by the time you have your pooled sample variance set up, you can combine those two into simply N1 plus N2 minus 2, because there's the minus 1 for each of them, thus minus 2 when you combine them. N1 plus N2 provided. So the denominator of your pooled sample variance formula is your degrees of freedom for an independent samples test. So once you find your pooled sample variance, this right here, you use that and you plug it into your standard error formula, which is going to go in the denominator of your test statistic. So it's just big square root, what you found when you did your pooled sample variance right there, multiply it by 1 over N1 plus 1 over N2, big square root of it, you get some number. That number is what you plug in for the denominator right there, and apart from that, it's exactly the same as the other formula, where it's just x bar 1 minus x bar 2 minus mu1 minus mu2, whatever you have in your hypothesis setup is what you do there. The x bar 1 minus x bar 2 is literally you have the mean for each of them, take the mean for the first sample, subtract the mean from the second sample, and it gives you this number right here, and then you just solve for it like that. So that's how you do for a mean-based problem for an independent sample. So let's move on to the next situation. Okay, so now in this situation, we're still dealing with independent samples where we have two different groups, each with their own treatments. It's not a match paired sample. But in this case, we're dealing with a proportion-based problem instead of a mean-based problem. So the formula for it, you still have to do several steps. You still have to pool the variance and everything, just like we talked about before. But instead, we're pooling the proportion and then finding a different standard error formula. It still represents the standard error, it's just a different formula for it, which will thus funnel into our test statistic. So let's take it step by step. We have our P pooled right there is just going to be N1 times F1, where the N's are the number of trials in your samples, the F's are the sample proportions, so not the population proportions, but the proportion that you actually found in your sample, or the F's right there. So it's N1 times F1 plus N2 times F2 divided by N1 plus N2, and that's going to give you your P pooled. Okay, so this right here, what you find for the standard error is going to funnel into the denominator right here. And so just like before, the base formula still applies for this situation here, even though we're dealing with a proportion-based problem. So it's still your sample information, so you're taking your sample proportion of the first one minus your sample proportion of the second one. Then from that, you subtract what you get when you get the population proportion of the first sample minus the population proportion of the second sample. Again, pi I've seen sometimes is p, so it's just the population-based information. All of that is divided by the standard error we just found in the second problem. So now we've gone over everything dealing with the independent samples test statistics. So let's wrap up talking about the matched paired sample test statistic. Okay, so finally we're wrapping things up with a matched paired sample. So you can see just based on how much less there is on the board, it's not nearly as complicated as the two sample independent sampling test statistics. So this should look really familiar because it's pretty much the exact same thing as what we went over in the very beginning of the video, touching back on the one sample test statistics for a mean. So instead of it being x bar minus mu divided by s divided by square root of n, it's just going to be d bar minus mu divided by s divided by square root of n. And that d bar right there, remember, when we're dealing with a match paired sample, what we're saying is that we have one group that we're introducing a treatment to, and we're seeing what the change was before versus after. We get that difference, we do that for however many things we're sampling in the test, and that's going to give us our average difference between the before and after consideration, which is your d-bar. So you literally just plug into that formula whatever the average difference was, subtract mu, which is going to be whatever you're hypothesizing about, whatever that difference might have been, divide that by your standard error, which in this case is simply going to be s divided by square root of n, your standard deviation divided by the square root of your number of trials. And then finally, one thing I want to point out is that for these types of problems, the degrees of freedom is going to be what you might be used to from before, where it's just simply n minus 1, because in these problems, we don't have n1, n2, mu1, mu2, because it's a matched paired sample on one group. So it is just going to be 1 n, 1 s, 1 mu, so on and so forth. So it's going to be the same degrees of freedom formula that we talked about before. So thank you all for watching. You know, when it comes to these formulas, I find that the hardest part about them is figuring out which one of them to use and which one to even begin with, because once you have the formulas laid out for you, it's literally just a matter of plugging into them. And sometimes it can be tricky to identify, okay, they're giving me this information in this problem, what variable does that represent? But for the most part, as you practice that and as you get better at that, it's just a matter of having all that information laid out, knowing which formula to plug into, then just plug and chug it. So I hope that gives you a good framework to work through those problems. Thank you for watching, and I hope that helped.